Today we are going to be introducing sound. This video will go more into depth into why we use certain formulas to describe sound, and will hopefully answer some of your why questions. Specifically, we will talk about what a sound wave is, how to describe it, and how temperature affects sound. The times where I start to talk about these specific topics are included in the description below in case you want to focus your review on one of the things I just mentioned. Okay, let's get going. So, a wave is a disturbance through space. We know that light can be considered in terms of wave motion, as can a slinky or a water wave, or sound. Sound is a mechanical wave, which means that it's able to travel without actually moving the medium it is traveling through from one place to another. So, sound disturbs air molecules and transfers energy, for example, but it doesn't transport the molecules to the other side of the room. A sound wave traveling through air or water is a longitudinal wave. This means that the temporary movement of air or water molecules is parallel to the direction that the sound is traveling in, like a slinky. Can you see how the compressed part of the slinky is moving or propagating this way? Well, that's what a single sound pulse would behave like too. Sound is basically just a pressure wave moving across a medium, and the regions of high pressure and low pressure get transferred until they reach our eardrums, vibrating them and causing our brains to interpret that as a sound. We often represent sound as a sine graph, with the amplitudes, or those high and low points on the graph, representing the highest and lowest possible pressures the sound wave can achieve. The bigger the amplitude, the louder we hear the sound. The wavelength of a sound is the distance in meters until the wave repeats the same pattern over again, represented on this graph as the distance between two like points, for example, crest to crest or trough to trough. We use the Greek letter lambda to represent wavelength. The period is the amount of time it takes this whole wavelength to pass by a point. And the frequency is its inverse, the number of wavelengths passing a certain point in a certain amount of time. We can literally represent these two values as inverse expressions, with frequency equaling 1 over period, and period equaling 1 over frequency. Now, before I move on, I want to clarify that this sine wave is not actually what a sound wave physically looks like moving through air molecules. Remember that sound is a longitudinal pressure wave. This sine graph is just a way for us to represent it in a more mathematically convenient way. Okay, so now we have a variable relating to a sound wave measured in meters, and we have something measured in seconds. Meters and seconds. Ringing a bell? We can get the speed of a sound wave. Because speed equals distance traveled over time, we can substitute the wavelength for the distance and the period for the time, because that's the amount of time it takes to travel that one wavelength or complete a full wave. So, V equals lambda, or wavelength, over t, or period. But remember that frequency equals 1 over period, and effectively, this equation is just wavelength times 1 over period. So we can actually substitute F in here, which is how you'll usually see the formula written. V equals lambda F, or speed of a sound wave equals wavelength times frequency. Simple, right? Well, not quite so. You see, a sound wave undergoes a phenomenon called refraction, which means sound waves actually change speeds and therefore bend a little bit when traveling through different mediums. Because the density of air is different at different temperatures, this counts as different mediums. What determines wave speed is the properties of the medium the wave is traveling through. Because warm air is not only less dense but also has less pressure than colder air, as the molecules are more spread out, these two effects will actually cancel each other out. As you can imagine, sound would travel faster in a less dense material because it's a whole lot easier to have enough energy to vibrate particles that aren't smushed together so compactly. But sound would also travel faster in a higher pressure material, almost as if the pressure was helping the sound wave push through the medium. However, we can't really vary pressure and density separately in a gas, because naturally, if we spread the particles out from each other, we would be decreasing both density and pressure. And if we pushed the particles together, we would be increasing both density and pressure. Because they have opposite effects on the speed of sound, their effects will cancel, leaving only one thing in air that can actually affect the speed of sound: temperature. Sound will travel faster at higher temperatures because the particles in the air are already vibrating. They already have plenty of kinetic energy, and they will be bumping and transferring that pressure wave more often and hence faster. We can use this formula: speed of sound equals 331 meters per second, which is the speed of sound at 0 degrees Celsius, plus the quantity of 0.6 meters per second per degree Celsius times the temperature, measured in Celsius, of course. If you're ever asked for the speed of sound at room temperature, or 20 degrees Celsius, you might just want to memorize that. That's 343 meters per second. Let's try a practice problem using what we've just learned. A sound wave traveling through air has a period of 5.7 milliseconds and a wavelength of 2 meters. What is the temperature of the air in degrees Celsius? Okay, what is the problem asking? We need a temperature value in degrees Celsius, and we are talking about a sound wave. Great, we have a formula for that. So what are we missing? Well, we are going to be solving for the temperature, T, and we're missing speed. So we need to find the speed of sound in this medium. Remember that every sound in this medium will have the same speed. They might not have the same wavelength and frequency, but the product of wavelength and frequency has to be the same. That's a nice tie-in to our next formula. We know that the speed of sound equals the wavelength times the frequency. We have the wavelength, but we're not given a frequency. We are, however, given the period, and we know that it has an inverse relationship with the frequency. Now, noting that our period is given in milliseconds instead of seconds, to get us to the standard unit for frequency, Hertz, we need seconds, because Hertz actually represents cycles per second, or inverse seconds. 5.7 milliseconds can be represented as 5.7 times 10 to the negative third seconds, and so we can set up our formula and solve for our frequency. We get about 180 Hertz if we round it to the proper number of significant figures. Now, let's plug all that into the speed formula. We get 360 meters per second, which will then plug into the formula that relates temperature and speed of sound. solving for temperature, we get a final temperature of about 48 degrees Celsius. So that's about as far as I'll go today in terms of the variance of the speed of sound. What I just talked about only applies to air. In terms of sound in solids or liquids, there's lots of complicated stuff that happens, so please let me know in the comments below if that's something you're interested in hearing about, but that's a topic for a whole other video. I hope that this video helped you. If it did, please share it with others, hit the like button, and subscribe for more physics, chemistry, and math-related content coming soon. Please let me know any questions you have in the comments down below, or any content that you'd like me to make in the future. Thanks for watching, and have a wonderful day.